So now we need to talk about how do we test the claim about some population parameter. So this first section is really about terminology and understanding those basics for hypothesis testing. The next section is going to talk about testing the claim for a proportion, and the last section will talk about testing the claim about a mean when we do not know the population standard deviation. So we're going to talk about that student t distribution again, and that's going to come up. I'm going to show you how to do one or two by hand. You've got two options with hypothesis testing. You can use something called the p-value method, or you can use the critical value method, which is called the traditional method. I'll show you on one of them both ways. You can choose which way you do it. I like to use the p-value method. So let's get started. When we talk about hypothesis testing, we have to come up with hypotheses. So we're going to have a null hypothesis and an alternative hypothesis. The null hypothesis is written this way. It's at h sub 0, and it's read as h naught. And it's the statement that we're wanting to test. The alternative is h sub 1, and we just call that h1. And it's the statement that we're trying to find some kind of evidence to support. So we actually have three ways this could possibly set up. It could be set up as a two-tailed test, a left-tailed test, or a right-tailed test. And it really depends on the claim that's in the wording as to which test you're going to have. So what we mean by two-tailed, if we were to draw a picture, everything's based around a normal distribution, whether it's the z distribution or the t distribution. Two-tailed means you've got some area in the tails that you're dealing with. So you're splitting that into both of those pieces. Notice that with a two-tailed test, that alternative hypothesis, that H1, is going to be a always equal to, a not equal to statement. If we have a left-tailed test, now we're talking about everything being in that left tail, so our picture will look like this. Notice that inequality is going to be a less than. And then if we have a right-tailed test, the inequality is a greater than, and it's going to force all of that area in that right tail. I also want you to notice that in every case, that h naught, h sub 0, is always going to be an equal to statement. So that's always going to happen. Now, the parameter for us will be one of two options. We're either testing the claim about a proportion, or we're testing the claim about the mean. And since we're testing the claim about a population proportion or a population mean, then we're going to use that P for proportion, or mu, which is that Greek letter that stands for population mean. So let's look at a few examples. If we look at this first one, we want to identify the null and the alternative hypotheses. So the mean annual income of employees who took a statistics course is greater than 60,000. So we're testing the claim about the mean. So there's our parameter we're looking at. And we're looking at greater than 60,000. So if we were to set these hypotheses up, you're always going to have two of them, H0 and H1. We're testing the claim about a mean. Notice they're giving us the alternative because they're giving us something that says greater than. So if that's our alternative, the null is always going to be an equal to statement. So it would say the mean is equal to 60,000. Let's look at 2. The proportion of people aged 18 to 25 who currently have COVID-19 is equal to 20%. So we're looking at proportion here. So that's the parameter we're looking at. And notice they're giving us an equal to statement. So to set up our hypotheses, we're using that P for proportion. Since this is the equal to statement, they gave us that null hypothesis. And we always want to turn the percentages into decimals. So the alternative is going to be not equal to. You're either equal to or you're not equal to in this case. So then 3. The majority of college students have credit cards. When we talk about majority, we're talking about more than half. So they're giving us the alternative hypothesis here. So the null hypothesis is going to be equal to 0.5. And then 4, the mean age of college students is less than 25. So they're talking about mean, so we're testing the claim about the mean. And it's going to be less than 25. So that means the null has to say equal to 25. In every case, that null needs to be written so that it says equal to 25. So now let's talk about what a test statistic is. The test statistic is a value used in making a decision about the null hypothesis. So we're converting some kind of sample statistic, like a sample proportion or a sample mean, into some kind of score. And for us, it's going to be a z-score or it's going to be a t-score, depending on if we're talking about testing the claim about a proportion, that's going to be a z-score, or testing the claim about a mean when we do not know the population standard deviation. In that case, it would be a t-score. So we're always making that assumption that the null is true, and then we're going to run the test. And then we've got to make conclusions based on that test. So we're going to see 2 different test statistics. We're going to see the test statistic for the proportion. It's going to look like this. And we're going to see that test statistic for the mean when we don't know the population standard deviation. It's going to look like this. Now, these should look really similar to what we talked about in in that last chapter with confidence intervals. We saw those formulas there. And it was built into that error, that marginal error formula. So they've come back now in hypothesis testing. And we've kind of talked about this before, that left tail and the right tail, or the two-tail test. There are 3 possible ways this could be set up. It really depends on that claim that's in the problem itself. So with the two-tail test, we're talking about a picture, and those pictures are going to be super important. That's going to look like this. So that region that's shaded over here is the critical region. If we're talking about a left tail test, now we're looking at what's going on in that left tail. So there's your critical region. And then the right tail test, we're talking about what's going on in the right tail. So there's your critical region. The p-value is the probability of getting a value in the test statistic that is at least as extreme as the one representing the sample data. So in other words, that p-value is really the probability of being beyond that test statistic in the tails. So then what we'll be able to do with the p-value method is compare that p-value with our significance level alpha. But before we go into that, I want to go back to where we wrote claims and look at whether we have a left tail, right tail, or two-tail test to kind of get used to this. This section is all about getting used to the terminology, and we're doing baby steps to help us build up to doing a full hypothesis test. So if we go back here, we're going to analyze whether we have a left tail, right tail, or two-tail test. So we've taken the claims and we've turned them into hypotheses for each one. And if we look at this one, this guy's a greater than. Because this is a greater than problem, then this happens to be a right tail test. So then when we look to find a p-value, that p-value is going to be everything in that right tail. If we look at number 2, notice that alternative is not equal to. Not equal to means it's two-tailed. So that means that our p-value is split up between the two tails. Number 3, we have a greater than again. So that is a right-tailed test. Right-tailed means our p-value is going to be in that right tail. And p-value is just an area under the curve. And remember, area under the curve relates to probability. So it's the probability of being beyond that test statistic. And then we look at this one. This guy is a less than. Less than means left-tailed. So we're going to get what type of test we have based on that alternative hypothesis. So let's talk about a few more definitions. We're going to see the definition of a critical region. I like to call this the rejection region or the rejection zone. So it's a set of all values of the test statistic that causes us to reject the null hypothesis. And it's going to have an area of alpha in the tails. The significance level, they're going to tell us in each problem what significance level we're going to use. We're going to use alpha just like we did in the last chapter. It's the probability that the test statistic will fall in the critical region when the null is actually true. And this is going to relate to a type of error that could happen when we're doing a hypothesis test. And then the critical value is any value that separates that critical region from the values of the test statistic. So the tails of the distribution are going to be the extreme regions that's bounded by the critical values. So let's look at finding critical values. Let's say we are looking at that first one. I'm going to call this one number 1. So we have a two-tailed test, and alpha is 0.01. And we're going to look for z critical values. So if we're looking for a critical value here, I like to draw pictures of what's going on. Because it's a two-tailed test, that alpha has to be split into both of those tails. So half of it has to go into the left, and half of it has to go into the right. So half of 0.01 is 0.005. So now we can find that critical value using StatCrunch. So we're going to go to Stat, Calculators, Normal, since we're looking for a Z. I'm going to find the one that's in the right tail. So I'm going to go greater than. So I'm going to type that area in the right tail there. Keep in mind, this is a standard normal, so the mean is 0 and the standard deviation is 1. And then we're going to compute. So we're going to get 2.58 as this critical number here. And since this is positive 2.58, and this is a two-tailed test, then the other one has to be negative 2.58. It has to be symmetric there. And this would be negative 2.58. So because it's a two-tailed test, we would actually have two critical values. Let's look at number 2. Number 2 is a right-tailed test, and alpha is 0.02, which means that entire alpha is going to be in that right tail. So to find that critical number, we're going to go back to StatCrunch. This is right tail, I need greater than. I need to leave this field blank. That's what I want to find. And I'm typing that area in here. And that area was 0.02. Compute. So we're going to get 2.05 for our critical value. So number 3, we're looking at a left tail test. Left tail means that entire alpha value is in the left tail. So we're going to go back to StatCrunch. Now I want it in the left tail, so I need to change that inequality. Hit 0.10, compute. We're going to get negative 1.28. So 4, 5, 6 are written a little bit differently. Notice they're giving us the alternative hypothesis, which means we know what type of test it is. So in 4, they're telling us the alternative hypothesis is a not equal to. And since that's not equal to, then that means two-tailed. So that alpha has to be split between both of those tails. Half of it has to go into the left, and half of it has to go into the right. So half of 0.05 is 0.025. This is going to give us 2 critical values. It doesn't matter which one we find. I'm going to leave it as less than and find that negative one. So if I hit compute, I'm going to get negative 1.96 for this. So if this side is negative 1.96, then this one has to be positive 1.96. Five, the alternative is greater than. This is a right tail test. So all of that alpha value will be in that tail. Alpha is always going to be in the tail. You just have to figure out if it's going to be split between 2 tails because it's a 2-tail test, or if you have to keep it all in 1 tail. So now we need to find that critical value. So I'm going to change this to a greater than so it's in the right. And our alpha value was 0.05. Hit compute, and we're going to get 1.645. So that's one of the few z-scores that tend to be rounded to 3 decimal places. And then let's look at 6. Because we have a less than, this happens to be left-tailed. So that forces that entire alpha value to be in that left tail. So we have a 0.05 there. And if we use StatCrunch, we're going to end up getting negative 1.645. So you can see how that alpha is related to that region in the tails. So that's called that critical region here. Anything that's shaded is that critical region. When we do a hypothesis test, we have 2 options. We can either use a p-value method or we can use the traditional method. I like the p-value method. I think it's pretty straightforward. So what we do is we find something called the p-value. The p-value is the probability of being beyond the test statistic. And we compare it to alpha. If the p-value is less than or equal to alpha, we're going to reject the null. If the p-value is greater than alpha, then we're going to fail to reject. The traditional method compares the test statistic with the critical value. So if the test statistic falls in that critical region is separated by the critical value. So if we look at our picture here, let's say this is our critical value. So this, because this guy's alpha. So if our test statistic falls into that region, let's say that test statistic is here. Maybe this had a 1.96 and we ended up with a test statistic of 2. Since it falls into that region, then we would reject the null. If it falls outside of that region, suppose we ended up with a 1 for our test statistic, and the critical value was 1.96, so that was our critical region. That 1 would not fall in that shaded region, so we would fail to reject H naught. Now both of these are going to give you the same result, so you get to pick which one you want to do. The p-value method works, the same way as traditional method. It's going to give you the same result because the p-value is the probability of being beyond the test statistic. So if we go back to this, suppose we did have 2 as a test statistic, then this probability is smaller than that red probability. So that's why we're going to reject, because it forces that test statistic to fall in that critical region. And likewise, if that p-value is bigger, going back to that, what if that test statistic was 1? Then that p-value would be this entire shaded region, which would be much bigger than what that area, that red area is. Which, if that happens, then that p-value, that test statistic, has to be outside of that red area, that rejection area. So I like to call that critical region the rejection region, because anything that falls in there is rejected. So keep in mind that when we're going through this process, our goal is not necessarily to prove the null hypothesis. We're only trying to determine whether or not there's any evidence to reject the null. So, and we always want to write that conclusion in terms of that alternative hypothesis. So I want you to think about the legal system and how that works. When there's some kind of trial, the verdict is always guilty or not guilty. We never say guilty or innocent because we don't have enough as evidence to prove innocence. We just prove not guilty. So this kind of works the same way. We're either rejecting the null hypothesis or we're failing to reject the null hypothesis. But that doesn't mean we are proving the alternative hypothesis. So let's talk about finding p-values. P-values are the probability of being beyond the test statistic. So if our test statistic is in the left tail and it's negative 1.25, let's draw a picture of what we're talking about here. So here's our negative 1.25. We're looking for this guy. So what is that probability? So we can go back to StatCrunch. We're going to change this to a less than. Now we have that number to type in here. We're going to type in negative 1.25. And my calculator won't let me type in negatives for my tablet. I'm not sure why. So if we were to do that, though, and I'm going to do that on my calculator. If we were to do that, we're going to get 0.1056 for that. So that p-value is 0.1056. Let's look at number 2. The 2, it tells us the test statistics in the right tail, and that value is 2.5. So if the test statistics in the right tail, this is a right tail test, we're looking at 2.5. That p-value is the probability of being beyond that test statistic. So it's really this guy. What is that area in that tail? So if we go to StatCrunch, where we want to be greater than 2.5, compute, and we're going to get 0.0062. Now, let's talk about the p-values and alpha again. So, if p is less than or equal to alpha, we're going to reject. If p is greater than alpha, we're going to fail to reject. Before we do any more, let's talk about what the conclusion would be for these. So on number 1, our p-value was 0.1056 and alpha was 0.05. So we do that comparison. 0.1056 is our p-value, 0.05 is the alpha. In this case, p is greater than alpha, so we would fail to reject. In number 2, the right tail test, we ended up with a p-value of 0.0062. The alpha is still 0.05. Our p-value is less than alpha, so we're going to reject. Okay, because p ended up being less than alpha. Let's look at 3. We have a test statistic and a two-tailed test, and z is 1.75. So notice they only gave us one critical value here, and that's fine. We know this is a two-tailed test because they tell us it's two-tailed. We have 1.75 for this guy. We can find this value. We know that what's in the left tail would have to be the same as what's in the right tail. We can use StatCrunch to find that value. So that area in that right tail is 0.0401. So if that's 0.0401, then the area in the other tail has to be the same thing. They have to be symmetric. So then our p-value is going to be 2 times 0.0401. Or we could just add those together, and we're going to get 0.0802. So now let's do that comparison. We have 0.0802. There's p. Alpha is 0.05. That guy's greater. And because it's greater, then our conclusion is to fail to reject. Let's look at 4. Notice this is not equal to. Not equal to means two-tailed. So they didn't have to explicitly tell us it's two-tailed. We know from that alternative hypothesis. They're telling us the test statistic is negative 2.75. So if this is the test statistic here, then the positive test statistic would have to be positive 2.75. They have to be the same number. It's just one's negative and one's positive. They do not have to give us both. We only need one. So now let's find the p-value. We need to know what the area is in each tail. So if we were to use StatCrunch, and mine won't let me type in negatives. I don't know why. I don't think Pearson likes me. So I'm going to have to use that right test statistic of 2.75. So we're going to get 0.0030. So if that's the area in the right tail, then the area in the left has to be the same thing. So then the p-value would be 2 times 0.0030, which would be 0.0060. So notice our p-value is less than alpha, because if we compare this to that 0.05, it's smaller. So that tells us we're going to reject. Now let's look at 5. So 5, think about what kind of test we have here. Because we have that greater than, this is a right tail test. So that means that p-value is going to be in that right tail. Our p-value, our test statistic is 2.3. We need that area in the right tail. So if we type in 2.3, we're going to get 0.0107. So if we compare p to alpha, there's our p-value. Alpha is 0.05. This guy is less than. If p is less than alpha, we reject. And then let's look at the last one, 6. So they're giving us the alternative, and it says less than, which means left-tailed. So that test statistic is a negative. We need that area in the left tail. So we could use StatCrunch. You would want to change this to less than, and you would type in that negative number. Like I said, this won't let me type in negatives. And we're going to get 0.0016 for that guy. So 0.0016 is our p-value. And that's less than alpha. Since p is less than alpha, we're going to reject.